Here we have two DC motors with their shafts going through a bearing and a pillow block. On top of the bearings are accelerometers to measure the vibrations in the bearings. This is a piezoelectric accelerometer with a single coax output that goes to the charge amplifier. As I hit the platform, you can see that the accelerometer picks up the vibrations. To measure the shaft speed, we have photo-optic sensors that pick up the reflective tape as the shaft goes by. This is sent through a Schmitt trigger and displayed on the oscilloscope. Here's the output from the photosensors, and from this we can determine the shaft speed. Here we have about 30 hertz, or about 1800 RPM. We can also use a strobe to verify the shaft speed. With this strobe we can manually change the frequency which it strobes. So we're at slow frequency now, and we can ramp it up until the shaft looks stationary. And right here, the colored marks that we had in the shaft look like they're about stationary. And reading from the dial on the strobe, we're at about 1800 RPM, which is the same as that we got from the oscilloscope. This is the raw signal from the accelerometer or the charge amp. This is the FFT or fast Fourier transform of the raw signal we just saw.
Here we can see some raw vibration signals and spectra of two example bearings. On the left we have a fairly good bearing, and on the right we have a bearing with some scratches and some problems. It's very hard to tell a difference between the vibration signals. They both look fairly random. But when you look at the spectrum, both bearings have strong low frequency components, usually due to some slight unbalance. But the good bearing, as you notice, has very little high frequency amplitude because it doesn't have very many scratches. And when you have scratches and defects, it generates a lot more high frequency noise in the vibration signal.